So hello everyone. This is the last session for the analog communications, and this session is more about the doubt clearing sessions. So there are some doubts that has been mailed to me by the students. I'm just going to describe all these problems once again. So the first question that somebody asked me, that it's very specific questions. Like first question is about what is power signal and what is energy signal. So what is power signal and what is energy signal, that has been truly already taught in the coursework. I'm just noting the main points between the power signal and energy signal. So basically, if you have a signal xt, so the energy of that signal, that energy is from minus infinite to infinite mod of xt square dt, and if the signal is a power signal xt, so the power will be limit t tends to infinite 1 by 2t from minus t to t mod of xt square dt. So this is for energy signal and this is for power signal. So what's the difference between the question is about what is power signal and what is energy signal. So for that, I'm just giving you a visual representation of this. Suppose you have a signal like this. From 0 to t. So if you integrate this signal over a region, this is the xt and this is the direction t. The y-axis is the values of xt, amplitude of xt. So if you take this signal and do a mod square from minus infinite to infinite, this is equivalent to doing the integration over the time 0 to t. So basically this is a time limited sort of signal, mod square dt. So this will come a finite quantity. Again, another type of signal can happen, that this signal just converges like this. So probably xt and t. I am just saying you the cases, like this should be for an energy signal, this should be less than infinite, this quantity. So what are the cases? For this case, it should be less than infinite, it should be finite quantity. And for this case also, it should be finite. Why? Because this sequence converges to 0. So as the time progresses, this signal tends to be 0. So that's why this is also an energy signal. Now suppose we have a del pulse here. So even if the amplitude at a particular instant of this del pulse is infinite, still the integration is 0 from minus infinite to infinite. If we take a del pulse, that is sort of 1, it will come. But now suppose I am taking the main example of a power signal. So what's the power signal here? Previously we have taken a signal like this. Suppose this sequence just have a negative direction like this, or this is like this. And dot 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 dot. It goes like this, this, this. Dot, dot, dot. Dot, 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 dot. 40, 40. So basically if you integrate over at minus infinite to infinite this sort of signals, this integration will not be a finite quantity, because it neither it does not converge, neither it vanishes after a particular time limit. It also does not converge to 0 as time progresses to infinite. So this sort of signal we just cannot calculate the energy like this. With this function, if we calculate this minus infinite to infinite, this quantity will be equal to infinite. So what we can do, we just take a particular duration for which it is periodic. So what's the periodicity? See, this signal, this value or this value just repeats after a particular time instance. And if we say that this total from here to here it is t, similarly this difference also t. So what we do over this particular time period, we just calculate what is the value of this integration. So for such reason we say what is the value of minus t to t, and then why we divide it over average over 1 by 2t, and t tends to infinite. Why? Because this is an infinite sequence. So for this sort of signal we say this is a power signal. Okay, so I'm just addressing the main questions here. So the next question was how to identify whether is a given signal is an energy signal or power signal. So just writing the main constant here. If you somehow can prove this quantity is less than infinite, this is an energy signal. If this is infinite, this, so now if it is infinite, this is not an energy signal. But not being an energy signal, does not mean the signal is a power signal. For example, I just do an example here. This signal, as t tends to infinite, xt tends to infinite, this signal is neither an energy signal nor a power signal. The condition of the power signal is this condition. This quantity should be less than infinite. This should be less than infinite. So these two conditions should follow. And you can calculate the energy and power in this way. Just the equations are given. You just take the functional notation of the signal and indicate over a particular time period if that signal is a power signal, if you feel that it is a periodic signal. If it is an energy signal, just do minus infinite to infinite. Now some attached question was like, what is ESD, difference between ESD and PSD? So what is ESD here? Just if there is an energy signal, this ESD measures the distribution of signal energy. This is the main part for ESD. That is somehow t square dt. This is the energy. So from Parseval's theorem, we just write that this is f square df. So energy is x of f square df, where x of f mod square is the energy spectral density. So how this distribution of this signal x t square, x f square, this is f, the frequency domain notation, this quantity is the ESD of the signal, and then we just integrate over minus infinite to infinite this quantity, and we can get the energy. So that is why this is ESD. Now for PSD, the key part is we know power signals, already discussed, have infinite energy, So in this case, ESD may not exist. This is due to the fact that, let's write in the Fourier transform may not exist. So in such cases, we can say that xx of f, that is the PSD, is equivalent to
गूगल क्या पूछा इस बार
t square dt is the power. We can calculate the power with this equation df. So as x of f, this term is the PSD here. But just see what is the difference here. X of f square is the ESD term here. That's the difference. So what is the difference between a power spectral density and energy spectral density? So energy spectral density will exist for the signals which are the energy signals, and power spectral density is the signal for which only power exists, right? So there should be a equivalent definition of xx of f for xt, and that we can write like it is a linear transformation, Fourier transformation, right? So basically all the equations remain same, but xt of f square only. So what is xt of f? Xt of f is like over the time period t, the signal will have finite, the signal will have a finite energy. So over that we can do the Fourier transform here. It may not exist that x of f, actually x of f may not have the Fourier transform, but xt of f will definitely have, because over a particular time period, this is a power signal, so over that particular time period it will have the particular it will have the Fourier transform. Fourier transformations will exist for this particular duration. So for this we can say this is the PSD. So that's the difference between ESD and PSD. So energy signal has energy spectral density, and if you take up suppose you are taking a sine wave or cos wave, those are the power signals. So actually power signals will have the power spectral density and energy signals will have the energy spectral density. And other questions are mostly we have solved in the previous cases, like what is the Fourier transform of the zinc, and all these things are already I have taught. So we are not going to do all these things once again. One question was like how to do the integration of 1 by 1 plus f square. So basically I'm just showing the steps, that it will be enough. And also false detection type of questions are there. Okay. Power efficiency. So basically the question said that transfer function h of f is 1 by 1 plus f square, and the input is a particular AWGN. So what will be the power at output? So at least we have also solved this question, but the integration I had not solved. So just let me solve the integration this time. I think the integration was the problem. So the one-sided power spectral density suppose this is a naught, and then this is given that 1 by 1 plus f square for one-sided. So it is one-sided, so we are not going to take the minus infinite to infinite. We are going to do from 0 to infinite instead of that, right? So we have to solve this integration from 0 to infinite. So let's solve the step by step. So we are going to use the integration reduction formula. One by 1 plus f square whole square df. So if you use the reduction formula here, you just can write it as just solve this integration. It will come 0 to infinite. One part is like this, and the another part will be, let me solve in the whole way. So just avoid these terms. We will use the terms in the end, the limits. So I'm just writing this integration reduction formula here. That can be written as so what is a b values we can write like from this equation that we know a is 1, b is equal to also 1, and n equal to 2. From this equation, comparing this and this, from that we can write this is equivalent to f by 2 into f square plus 1 0 to infinite plus 1 by 2 1 by f square plus 1 df 0 to infinite. So this term will not exist because for 0 this is 0 and for infinite the denominator is 1 by infinite is 0. So this terms comes to 0 and this comes like tan inverse f 0 to infinite by 2. So that is pi by 2 by 2. So that is pi by 4.
Thanks much.
The answer is pi by 4 in this way if you can solve the integration. So once again I am repeating this that this is from 0 to infinite 1 by f square whole square df. So we are using this particular standard formula of integration reduction formula, that is 1 by a f square plus b whole to the power n. Then if we apply this reduction formula and do some integration, it will come like this formula, the reduction formula, plus c for an indefinite at. So we are going to do a definite sort of thing. So basically you can say this comes from 0 to infinite and this is 0 to infinite without using this c term, and then we just solve this equation. So in this way if you solve, it will come pi by 4. And another question was, what is the small scale and large scale error model of PLL? So for that small scale for this there are many standard books. Or PDFs. Mainly this depends on what is the steady state error type of thing. So you can follow the control system books where the phase lock loop systems errors and all these things are already described there. So that's the big analysis, error analysis type of thing, and you can find it there. That's not a big thing. One more question was, what is false detection and for a random variable. So let's discuss that. So question was like that, what is the false detection? So suppose we are just going through a hypothesis testing. So suppose there is a signal that is equal to y is equal to x plus w. So where is the randomness here? So suppose x can take the value 0 or x can take the value 1. These two values x can take. Now we have to comment whether x is 0 and 1. So where is the randomness? Randomness is w. W is a Gaussian noise. with 0 mean and some variance sigma square. Now, what is the case here? So, the first case, if the signal is not present in the system, so what will be the output? This will be the output, and for x equal to 0, we can say the signal is not present, and only W is the output. So probably this is the W with 0 mean. So the noise has the 0 mean thing, so 0 mean and sigma square. So that Gaussian distribution I have drawn, and this is the axis of Y. So this is the distribution of W. Now suppose the signal is present, x equal to 1. So a constant term is getting added with W. So that is 1 plus W. Right? So in this case, the distribution will be the same distribution, but just a simple change, that so it is for x equal to 1 and y equal to 1 plus W. Similarly, this is for x equal to 0, y is equal to 0 plus W. So now suppose you just made a decision over here. This is the decision region. So you have to comment whether the signal is present or not. So suppose we say this as VTH. So if Y is, suppose we receive a Y value, and if this Y is greater than VTH, for this we say the signal is present. So we obtained some signal here in this region. Suppose this is above 0.5, VTH is 0.5. So suppose we receive a signal that is greater than, we receive 0.6. At that case, it is greater than 0.5. So we can say that the signal is present. Suppose we receive a signal 0.4. So at that case, we will say the signal is not present. So what is the condition for signal is not present? VTH. So in the next line, by drawing these things once again, so basically both are Gaussian with same variance, and for this the mean is at 1 and this is the point 0. So suppose we receive a signal Y at 0.8. So there could be two possibilities, like y is equal to x plus w. Now suppose x equal to 0 but the noise is 0.8. So at that case y will be 0.8, but our threshold in this point was VTH was 0.5. So we will say that y is greater than VTH. So we will conclude that signal is present. However, in the real scenario, we can see that suppose x equal to 0, but at a particular instance w is taking the value 0.8. So that noise is corrupting the actual output to 0.8. So this is a false detection. So why it is false detection? Like the actual x equal to 0, but we are finding out that x equal to 1, that is the decision over this, that y equal to 1. So this is the false detection. So what is the probability of that? This area under this red curve. For this curve, for this particular region, suppose VTH for this Gaussian curve, we have to calculate what is the area under this curve, and that is the probability under which the false detection can happen. Because see, this is the curve for the signal is not present, but the small tail is just exceeding this part from VTH to infinite. So we have to do the integration from VTH to infinite over this Gaussian. And that will give us the what is the probability that this false detection can happen. Similarly, if you take a uniform distribution also, you can the curves will be like this, and the black curve will be like this. And suppose you are going to take the decision region here, so this small region will be the probability of false detection. So according to that, you have to calculate what is the probability of false detection. Okay, is there any more thing that I can ask? And this power efficiency of an AM signal, that is also taught in the classes, so you can just reconsider those videos once again, and it will be easier. So just how to calculate the, just I'm writing this thing as the question is there also. Power efficiency of AM signal. with an example. So just I'm giving you an example. So suppose you are given a modulation index. I think everybody knows what is the modulation index here. So that is 0.6. So if you can find what is the modulation index, that is actually AM by AC. So you can calculate the efficiency as is m square by 2 okay, this is the efficiency. So basically you have to think what is the actual ratio.
Yeah, so I have a question here. Using the same formula, I had solved the problem, but
Okay.
it was marked as incorrect.
Which one? I don't know that one. Like
This efficiency thing only in the solution, the answer was something else.
okay, so I actually don't know which question you are referring. So
No, this
but
efficiency, power efficiency of AM only I'm talking of.
had I solved that
I think
question in
one
the
of the solution, the answer was incorrect. That's what I am feeling.
okay, so you can write it to the like in the NPTL. Actually, I'm not
Oh, okay.
okay. So maximum I can help you what about the concepts. Like I'm not checking the actual answer
Okay.
sheets.
Okay, fine, fine. Thank you.
So mostly all the things are covered right now, except that small scale error and large scale error you can find actually in the PLL. Like you can read anything about the PLS. Like that is the error analysis type of thing. So that cannot be covered within 1 hour. So that's the thing. You can
Okay.
just find it any slides on any PPTs also you can find it. It's not a big thing. Like
Okay, fine.
you just find it. And other things I have already discussed. And power signals and energy signals, what is the question about them? Like these are the very well-known topics, right? So what was your particular question? May I know?
Yeah, it's okay, sir. Yeah.
Okay. So last question was about stationary process and white sense stationary process. That's the last question that is left till now. So I'm just writing the definitions once again. First, it is strict sense stationary. So suppose xt is a random process. Now I just take two pairs, x of t1 and x of t2 at two different instances. And I also take another pair, that x of t1 plus c and x of t2 plus c of the same random process. This is the particular random process, and these are the xt1 after time c, and this is xt2 after time c. So in this scenario, we can say that the process is nth order stationary if the joint probability distribution, that can be written as this x1 comma x2. In this way I am taking xn. So here I had taken like xt1 and xt2. In this way I can go to up to tn, nth order, and then t1 comma t2 comma dot 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 tn. So basically is equivalent to taking the same defined random variables with different time instances, like x1 comma x2 comma dot 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 xn, and their time shifted versions t1 plus c, t2 plus c, dot 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 tn plus c for any c. If this holds, this condition holds, then the strict sense stationary process is the nth order stationary process. So the first order stationary process will follow this rule: f of x comma t c for any c. And if we think about any second order, it will be x1 comma x2 and t1 comma t2. This pdf will be equivalent to x of x1 comma x2 t1 plus c and t2 plus c, similarly for any c. So this is first order. And this is second order stationary. So x1 is also, I'm just for clarity I'm just writing x1 is equivalent to, maybe people can confuse them as different random variables, but this is not, this is coming from the different random variables for, but they are of the same random process. So at every time instance there will be a random variable, and that representation x1 is equal to x1 at t. So x1 is the random variable at t equal time t for random process x of t. So at time t1, sorry, this time t1 it will be So basically x1 is the random variable of the random process xt at the particular instance t1. So at particular t1 instance, if we sample that random process, we will get a random variable x1. Similarly at time t2 we will get this random variable x2. Similarly I will get tn. And for wide sense stationary, we are just writing it. For a WSS process, if xt is the random variable, we have to get two following conditions to be satisfied. The first is mean of this random variable will always be constant, independent of time. So even if time changes, the mean of the particular random variable of the random process will not be changed. So at each interval, like at the time increases, this xt will give x1, x2, x3, all these things, and their mean will not change. Their mean will remain mu. And another thing is x of t1, x of t2, it will be dependent on the time difference between t1 and t2. It only will depend as a function of t1 and t2, nothing else. So if these two conditions happens, like mean is constant and this autocorrelation function is only the difference between the time indices, then we can say that the process is a wide sense stationary process. Okay, so I don't think there are many more questions to this session.
Can we get the recording of this session as well?
Yes, I will update in my YouTube channel.
Yes.
You can
And also in NPTL thing, right?
I'm not sure about what will happen to the NPTL, but at least where you are finding all those videos, I'm going to upload all these things.
Yeah, I am checking those videos regularly. So in the same, is it? Okay.
Yes.
Yeah.
Okay. Best of luck for your exam.
Yeah, thank you.